Welcome to the next session of Strength of Materials 1. In the previous class, we have completed our unit's first part, which is flexural stresses or the bending stresses. Now we are going into the new concept, that is shear stresses. Okay. Firstly, in our bending stresses condition, there we have observed a concept, pure bending, right? So what is the meaning of pure bending? In case of pure bending, what is the thing happening? I am considering the section itself is having purely the bending moment, but not at all any shear force, right? So in pure bending condition, I am taking an assumption like some part of the beam which is subjected to constant bending moment and with zero shear force. Yes, the section with the constant bending moment and with the zero shear force, such a type of section only I am taking and using the pure bending theory equation. There I have taken net shear force is equal to 0. That's why our derivation for the m by I is equal to sigma by y is equal to E by R can have generated. Now, in practically, there also we have mentioned practically any segment without shear force and having constant bending moment is not at all possible. That we call it as a practical condition. Okay. So that implies shear stress will be 0. So we are calculating the bending stress only from that condition. But in actual practice, due to the different loading combinations, different loading conditions, the bending moment and shear force are varying along the length of the beam, right? When we observe any type of loading, when a simply supported beam with a point load, so I have written the shear force like this, but the bending moment is like this. So from section to section, the shear force and bending moment are changing. So whatever is the loading combination, generally we will observe the shear force and bending moment are varying along the length, right? So in pure bending, I am considering shear force is equal to 0. So I have considered the shear stress is equal to 0 and the bending stress is only we have calculated it. But here generally shear stress is also existing because the shear force is also there for every section due to the loading combinations. It causes bending stresses as well as the shear stresses in the beam members. So it causes bending stresses as well as shear stresses in the beam members. The shear force is acting on the transverse sections, that implies shear stresses will be along the transverse sections. So firstly, what is a transverse section? When we observe a beam member like this, and when you see it is having a body like this, when we cut the cross section along the length with some plane, so this is the cutting edge. When we cut that section and when you observe the cross sectional view, that we call it as transverse section, this is a longitudinal and those sections which will come for us can be called as transverse sections, and the shear force is acting along the transverse sections only. Similarly, shear stresses will also act along the transverse sections, as the shearing force is acting along the transverse section. Corresponding shear stresses also will act along the transverse sections. The shear stress produces complementary stresses. So we have already mentioned the condition, principle of complementary shear stresses. When we observe a single body is being subjected to some shear stress, so the complementary shear stresses will be generated by the shape like this, which is causing the distortion like this. So as it is, they are causing that, we call it as the complementary shear stress, the generation of complementary shear stresses. So even I am producing a shearing force along the transverse sections, it will cause shear stresses along the transverse sections only. But due to this transverse sectional shear stresses, some complementary shear stresses will be generated acting along the longitudinal layers, right? So along the transverse sections, the shear stress is generated due to the shear force. Along with this, due to the complementary principle, some shear stresses with the same amount like this. So the same shear stress will act along the longitudinal layers also. Due to this shearing force F action, tau is generated, and due to this tau along this direction, this tau is generated. Okay, so the shear force at a section is causing shear stress along the transverse section, and that shear stresses are having complementary stresses and they are applying on the longitudinal layers of the beam member. So this point is important for us. Why? The shear stress is like this. Even though the shear force is like this, it is causing shear stresses in this direction only. But complementary shear stress principle is there. That's why shear stresses are generated in this direction. Okay, the shear stresses are generated. Now I am going into generate or give the formula for shear stress at a section. We have given bending stress at a point. Okay, so when we are observing the cross section, so being it a beam, and when we cut the section and see the cross section, at any point I need to calculate what is bending stress. Okay, for that we have taken neutral axis and that position we have indicated with respect to the neutral axis, and using this we have calculated sigma is equal to m by I into y. So bending stress at a point we have calculated. Here also shear stress at a section I am calculating using the conditions from the basic principle. Okay, so the previous derivation we have gone through this and we have got this term, and we are going into the shear stress calculation. Okay, consider a simply supported beam which is being subjected to UDL, and due to that UDL, the shear force and bending moment are varying along the section to section along the length. So a simply supported beam which is being subjected to UDL over entire length. So due to this intensity of the load, what is happening? What is the shape of the shear force diagram? As it is W, it is WL by 2 and WL by 2, and it is observed like the shear force is varying like this, and the corresponding bending moment diagram is like this. So from section to section the shear force value is changing and the bending moment values are also changing, right? So the height of the shear force diagram, the height of the bending moment diagram indicates shear force at the section, bending moment at the section. Okay, so due to that UDL along the length of the beam from section to section the shear force is varying, along the length of the beam section to section bending moment is also varying. So in pure bending condition what we have taken, having the zero shear force and constant bending moment, but actual practice these cases may occur. That's why from section to section some shear forces and bending moments are varying. Such a type of loading I have taken here. Okay, so we have considered a simply supported beam and it is being subjected to a UDL. Okay, and let be this is the depth of the beam. When we see the triangular or the isometric view in the side, you can observe this width of the beam, right? So width of the beam, depth of the beam, and along this is length of the beam. This may not be needed, but only for our indication, a rectangular bar. Okay, it is having 3 dimensions. Firstly, I am seeing the length and depth only, and when we see the side, you can observe the width of the beam. Okay, such a type of beam we have taken and we have applied a UDL of intensity something. Okay, so UDL of intensity W per unit run. Okay, in that beam, consider two sections AB and CD which are at a distance of dx apart. Okay, so on this length I am taking two sections AB and CD which are over a distance dx along the length, that is the dx distance between the two sections. Now the shear force at section AB line, F is indicated as the shear force, M is indicated as the bending moment. As we have already said, from section to section shear force and bending moment are varying. So at the next section I am taking some other value is the shear force, some other moment is the bending moment, because values of shear force and bending moment are varying, whether increase or decrease, that is not at all a problem, but it is varying. Okay, so And the next section CD, I am observing at the CD section, F plus DF is the shearing force, M plus DM is the bending moment. This plus DF and plus DM may be negative values also, but some change has happened. That is the indication of this. This is F and M. This is F plus DF and M plus DM. Okay. In this way, we have calculated our shear forces and bending moments. And we have indicated capital I as moment of inertia of the section. Just now we have given the beam is having the cross section like this with the B and with D depth, right? And due to this cross section, BD is there, right? So this one is D and this one is B. For this, I have indicated moment of inertia as capital I. For the rectangular beam, what is the moment of inertia when it is having B width and D depth about the neutral axis? Okay, so simply a rectangular bar where the neutral axis is being located, it is located at half the depth, right? So the neutral axis for the section is at half the depth. And about this neutral axis line of this transverse section, the moment of inertia is BD cube by 12, which is equal to BD cube divided by 12. Now, I am considering the segment separately. So, this is the whole beam which is being subjected to UDL. There we have taken two sections, that is AB and then there is CD. In between those two sections, we have taken a length or the distance apart as dx. Okay, so this is the dx length. Okay, now when we see only the quotient, removing all the external things, only I am keeping that segment alone. Okay, that segment only there with me, and I am indicating F, M, F plus DF, M plus DM on the section. Okay, so this is the section, AB line, CD line. This continuation is indicated like neutral is there. Okay, so this one is neutral layer along the length of the beam. So this is the neutral layer along the length of the beam, and AB section, CD section in between the dx distance, and on the left side we have indicated M, on the right side I have indicated M plus DM. As in a simply supported beam with UDL over entire length, what is the bending moment diagram? It is like this, right? Completely sagging type moment. Either it is 0 or some value, but it is purely sagging type. That's why it is having pure sagging type indication. That's why these two curves, it is causing sagging on this section and it is causing sagging on this section. So both are indicated like this because a simply supported beam with UDL over entire length will have a complete positive bending moment over the entire length. That's why these two arrows were like that. Okay, this one on the right side is causing sagging moment. This one on the left side is also causing the sagging type moment. Right? And just up to that you should have to observe. And the next thing, we need to calculate shear stress on the section AB at a distance y1 from the neutral axis. Okay, so on the section AB, then we should have to know that we should have to generate the section diagram. This one is section AB and having a width B and the depth D. What it is indicating? This is the cross-sectional view of AB section. Okay. And on this cross-sectional view of AB, what I need to do? I need to calculate shear stress on the section at a distance y1 from the neutral axis. So firstly, I need to indicate the neutral axis line. So where is this neutral axis line is located? As the section is symmetrical, it is a rectangular one. So the neutral axis is passing through the geometrical center. Geometrical center means total depth by 2. So the neutral axis is at D by 2. Okay, so the neutral axis is at D by 2 from top, D by 2 from bottom. And from the neutral axis, at a distance y1, we are calculating shear stress on that point. Okay. We need to calculate shear stress on the section AB at a distance y1 from the neutral axis. On the cross section of AB, consider a line EF. Okay. So, on the cross section AB. So, this is the cross sectional view of AB line. So, along the length of the beam, it is there. And when I am cutting and seeing the cross section view, that cross section is like this. Okay. So, this is the cross sectional view of the cutting section AB, and I have observed B width and D depth. There, on the cross section of AB, consider a level EF at a distance y1 from the neutral axis. Being it as a symmetrical section, I am taking this neutral axis is at d by 2 from the top layer as well as from the bottom layer also d by 2. Okay. Now, consider the portion above the line EF in between the sections AB and CD. Okay. Now, I am considering the portion. See here, only I am considering the rectangular portion. This one is AB's section, and over a length of dx, so if this is a length of the segment dx and it is having the width as b and having the depth as d. So this is the indication for AB section, and the next side is indicated as CD section. So now consider the portion between this EF line, above the line EF. Just now we have indicated EF line here, right? So this is EF, as this EF line will be continued. Okay, so up to that, above that portion I am indicating only this dx portions front. When I see the AB section, I can observe EF line, and when we cut the section like that, so above the level EF on the sections between AB and CD. Okay, this is the indication we have done. Don't think all the terms, those will be added later. Only the first term which are explaining this is, we are considering the portion between AB and CD and considering the portion above the level EF in between those segments. So completely those top portion like that, as the section is completely with a solid, and the top portion I am considering. This part of the beam is consisting of infinite number of cylindrical elements. Each is having the cross-sectional area as a dA and having the length as dx. So what it is saying, as it is being like this. Okay. So this is the complete portion we are having. When we see the solid like this, so this portion is the complete single solid like strip. Okay, nearly the combination of 2-3 layers, like you can assume. Okay, so that layers or the portion I am considering. In that portion, I can consider so many number of cylindrical elements with a cross-sectional area dA and having the length as dx. So this is the portion, and I am considering many number of cylindrical elements will be there in that. Okay, we are assuming like this. Each member is continued. Okay, this cylinder is continued to this, and this cylinder is continued to this. So many number of cylindrical elements, like a bunch of wires are having semi wires in that, right? Those copper threads. So number of cylindrical filaments or the wires or the cylindrical elements will be there, and each is having area. Okay, each cylindrical element is having some cross-sectional area, right? That cross-sectional area of the each cylindrical element I am indicating as dA. And what is the length of the cylindrical element? dx. So dA is the length of the cylindrical element and dx is the dA is the cross section area of the cylindrical element and dx is the length of the elements. Okay. Now consider any one of the elemental cylinder in those lines. Okay. So which is at a distance y from the neutral axis. Now we have taken the cross section AB and there we have indicated neutral axis and we have indicated the level EF and the level EF is at a distance y1 and this is having so many number of cylindrical elements. In those I am considering one such type of cylindrical element which is at a distance y from the neutral axis. Above the EF, so many number of elements will be there which are being continued. Okay, so which are being continued throughout the length. In those elements above the level EF, I am considering one cylindrical element which is at a distance y from the neutral axis. Okay, that we have indicated y from the neutral axis. So this is the cross sectional view of AB. Back side is the cross sectional view of CD section and having the width B, total depth D and having the length dx and indicated the level EF and the level EF is at y1 distance and above the level EF so many cylindrical elements will be there, each are having area dA and having the length of the cylindrical element as dx. In those type of elements I am considering one element cylindrical. That cylindrical element is at a distance y from the neutral axis. Okay, so that cylindrical element is at a distance y from the neutral axis. If we consider that cylindrical element okay, so that is indicated like that. This cylindrical element is continued. Number of cylindrical elements were there. In those I am considering one such type of element. For the elemental cylinder which is at a distance y from the neutral axis, let dA be the area of the elemental cylinder, dx be the length of the elemental cylinder and y is the distance of the cylinder from the neutral axis and sigma be the bending stress on the elemental cylinder on the section AB and section 1, 2 or section A, B, C, D we can indicate. Throughout I am taking only one thing, that is section A, B and section C, D, right? Okay. Sigma is the bending stress on the elemental cylinder on the section A, B and on the other side, just now we have said the bending stress is varying from, bending moment is varying from point to point. That's why bending stress sigma also will vary from point to point, right? So at the section CD level, what is the bending stress acting? That answer I am indicating as sigma plus d sigma. Point to point, m is changing, right? So as the m changes, sigma changes. That's why m is different at some other point. That's why the corresponding bending stress I have indicated as sigma plus d sigma. M is changing, stress will change. Bending moment at the section changes, the corresponding stress will change. Okay, so the bending moment at the section is m plus dm. So the corresponding bending stress is also should have to change. That I have indicated as sigma plus d sigma. And this is the overall indication. And on this portion, I have indicated sigma as the bending stress. And here that is sigma plus d sigma. Into dA I have indicated. Later you will get what is into dA. Okay. So only on the AB section stress is sigma. On the CD section the stress is sigma plus d sigma. That only you should have to remember. This is the whole picture. You should have to observe what is happening. Bending stress at a distance y from the neutral axis on the elemental cylinder at the section AB. Okay. So just now we have said AB section is there and the cylindrical element is there and that cylindrical element is at a distance y from the neutral axis and this section AB is having the bending moment as m. Okay, so distance of the point from the neutral axis is y, having the sectional moment as bending moment as capital M, and the overall moment of inertia of the section we have indicated as I. Now for this combination, can I calculate bending stress acting at the point? bending stress acting at the point is equal to sigma is equal to m by I into y. Okay. So bending stress acting on section AB. Similarly on the section CD. So on the other side, the section, another section is also there, right? So on that section, so on the next section, what is happening when I am observing that section? This is the cross section view of the CD line. So here also the same cylinder is continuing, but this indication is for the CD section. Again I am taking the element, but on the CD section moment is m plus dm, and the corresponding bending stress what we have given on this section, that is sigma plus d sigma, and the moment of inertia of the section same BD cube by 12 only. So again I, what is the position of the point we are calculating the bending stress, which is at a distance y from the neutral axis. So for the bending moment having moment of inertia of the section as I, and the point I am considering is at a distance y from the neutral axis. So the corresponding bending stress on the section CD, okay, bending stress at a distance y from the neutral axis on the elemental cylinder at section CD is equal to sigma plus d sigma is equal to m plus dm by I into y. Okay, this is the bending stress acting on the section AB at a distance y from the neutral axis. Similarly on the section CD at a distance y from the neutral axis. So section AB is having m moment, section CD is having m plus dm moment. At AB, sigma is the bending stress. At CD, sigma plus d sigma is the bending stress. And from the neutral axis, y is the distance. From the neutral axis, same y is the distance. And moment of inertia is I. Here also the moment of inertia is I. In this way, the plane AB and the plane CD, which are at a distance dx, were indicated. Now, the corresponding forces. So, what do you mean by force? Force is simply is equal to stress into cross-sectional area. As our bending stress is acting, that is sigma into dA. What is the area of the elemental cylinder at the portion? That is dA. So, the force acting on the elemental cylinder at the section AB is equal to sigma times dA. So, stress acting into cross-sectional area of the element. Just now we have got the derivation m by I into y as sigma in the previous step. So, the bending stress acting on the section. And the force acting on the same elemental cylinder but at the section CD level. Okay. So, at the section CD, the corresponding answer is sigma plus d sigma into dA, because area of the elemental cylinder will not change, but from point to point bending stress what it is, that is changing. And the corresponding answer for sigma plus d sigma is m plus dm by I into y. Substituting that part, we have got m plus dm by I into y into dA. Now, these two forces are acting on the same elemental cylinder, right? So, then I observe the section on the complete left portion, AB section, we have got the stress as sigma times dA. And of the same element on the next section, we have observed sigma plus d sigma into dA as the force. So, the same elemental cylinder is facing one type of force here, another type of force here. So, these two forces are acting on the same elemental cylinder. Okay. At the two ends of the cylinder, the forces are different but acting along the same line. Only they are acting along the same line, but the amount from this value, from this direction, and the amount in this direction, they both are different and acting in the different directions, as the corresponding moment is like this and it will cause the stress like this, and there the corresponding moment as m plus dm like this and it will cause the stress like this. So, this is a sigma and this is sigma plus d sigma, and multiplying into area and multiplied into area. And these two forces are acting on a same element in the same line but in the different directions. So, the net or the unbalanced force will come out. Therefore, the unbalanced force that is acting on the elemental cylinder is equal to one side force minus other side's force. So, force acting in one direction minus force coming in the another direction on the same cylinder. Okay, m plus dm by I into y into dA minus m by I into y into dA. So finally we have got the term as m by dm by I into y into dA. So this is the unbalanced force acting on the only cylinder. Okay, then I am taking this section and considering only one cylinder, and on the left side we have got the portion and we have got the same cylinder's other end. At this end we are applying some force, at the other end I am applying another force. So on the same elemental cylinder, the net or the unbalanced force still acting is dm by I into y into dA. Okay, so the total unbalanced force we should have to calculate. Okay, the calculation of the total unbalanced force we will continue in the next topic. So until then, please revise this concept. Thank you.